figure because it summarizes a lot of different things. So, this over here with this arrow leaving the cell, this is gluconeogenesis. So we're in a hepatocyte right here. This exit indicates that we're leaving as glucose, right? And we know all about gluconeogenesis. Once it gets into the bloodstream, why we've asked for gluconeogenesis. These are amino acids. This is what happens to them when they enter the liver. They have a couple of different choices. So they get converted to alanine, and alanine gets converted to pyruvate. At the same time, alpha-ketoglutarate gets converted to glutamate. So, is alanine an amino acid?
Yes.
Yes. Is pyruvate an amino acid? No, it's a keto acid, right? Alpha-ketoglutarate is a keto acid. Glutamate is an amino acid. We just did a transamination reaction. Okay, so that happens so we can switch them. Now we have pyruvate and glutamate. Pyruvate can go into the mitochondrion. It can do some other stuff too, right? This is kind of a shorthand for going through the Krebs cycle because you get all the way out to oxaloacetate. Oxaloacetate can become aspartate. Glutamate, and this is what you're drawing, can become alpha-ketoglutarate. Is glutamate an amino acid?
Yes.
Yes. Is alpha-ketoglutarate an amino acid?
Keto
It's a
acid.
keto acid. So oxaloacetate goes to aspartate. Aspartate is an amino acid, so oxaloacetate, if we go back to 12 and look at the structure, here's oxaloacetate. What does that look like to you?
Keto.
A keto acid. Remember, it's a keto acid in the middle because it has the C double bond O. So we're transaminating again. And that exact thing is why I'm having you draw that on the quiz. Because it will make more sense if you literally just go through it, to reference Dr. Tam again, it's pedagogical. Anybody heard that? I don't know if he still says that. That you'll see it as you do it. So, okay, so we're down here. Now we've got this aspartate. This is an amino acid which can be exported out of the mitochondria, and it can hop into the urea cycle, and then the urea can leave. So it hops up here in the middle, right? And then you go to arginosuccinate, and then you have a couple choices. If you need to do gluconeogenesis, you can hop out and become fumarate, malate, oxaloacetate, which are all Krebs cycle intermediates, and then you follow this pathway, and there's gluconeogenesis. At the same time, bless you, you get rid of the nitrogen by following through in the urea cycle. So, you've asked for gluconeogenesis, right? There are two things that have to happen. If you want to make it from amino acids, you have to go through this process. So you're making the glucose, bless you, but you also have to get rid of the nitrogen that was attached to the thing that turned into the glucose. So that's what this whole giant process is about. And so especially if it's coming from the muscle, right, if you're bringing alanine from the muscle is a huge consumer of energy under work conditions, even under non-work conditions, but especially under work conditions. So if you're making alanine, let's go back to our that great muscle picture. Right? If you're making alanine in the muscle because you're going glucose to pyruvate and then you end up all the way down in alanine, you're exporting it to get more glucose. The muscle is providing the liver with fuel to give it more of what it wants. The muscle wants more glucose, so when it exports alanine, it turns back into glucose. And there's this really complex relationship between when we do work, we actually break down muscle, right, and then it gets put back again stronger, and that's why you need amino acids, especially after you work out, because you need to have that amino pool high so that you can rebuild the damage. But while these things are breaking down, in order to run all these breakdown reactions, you need energy. If you need energy, you need glucose released from the liver, either by glycogen breakdown or by using new amino acids, or eventually you turn to fat breakdown, and we're going to get there. But that's what this whole process is about. It's dependent on what you're asking for. You the muscle, you the body, you the hormone, you the whatever. Whatever the signal is being sent, this is going to happen, to varying degrees, right? It's always probably running maybe 5%, 2%, 1% of the time. But under work conditions, the more amino acids you import, the more alanine you're importing, the more you're running this cycle and getting gluconeogenesis to occur. Is that making a little more global sense? All right. That's
So an amino acid can go in and out and then become a glucose.
yes,
So
yes.
going in, they're always glucogenic.
So not all of them are. In other words, so this kind of shorthanded this. To be gluconeogenic, it depends on whether, let's see if we can. They're not all directly, right? If you can convert it, if you're doing the alanine cycle and you convert it to alanine and then you go through this whole system, right? If you go down all the way here, yes. But this is more expensive than this. This is saying pretty much directly, you either hop into the citric acid cycle or you don't.